In this video, I'm going to find the derivative of three functions here that involve logarithms. So these are sort of what I consider essential problems that demonstrate the derivative of functions with logarithms. So let's just do an aside where we begin with a reminder that the derivative of ln x is equal to 1 over x. It's a really nice, simple formula. All right, for this first one, what I see is that there is a composition, y equals ln u, where u is the inside function of 4x cubed plus x. Okay, so I see that composition, and I'm going to use the chain rule. That's what we do when we're differentiating composition. So when I have a composition of two functions, the chain rule says take the derivative of each of those two functions and multiply together. So the derivative of ln u is 1 over u, which I'll write down first when I do the derivative. Take that derivative. So 1 over u, that's the derivative of ln, whatever, is 1 over 4x cubed plus x. So I'm going to just go ahead and not write u, 1 over u, but 1 over 4x cubed plus x. And then I multiply that by the derivative of what's inside. The derivative of 4x cubed plus x is 12x squared plus 1. And what I see is a fraction as my final answer, where the denominator is the inside function and the numerator is the derivative of that inside function. And that's what you see when you take the derivative of logarithm of a function. So that's the first one. So it's the chain rule. 1 over what's inside times the derivative of what's inside. Now for the next one, I am going to use properties of logarithms. Which ones am I going to use? Well, these are some properties here. ln a times b is equal to ln a plus ln b. ln a divided by b is equal to ln a minus ln b. ln a to the t power is t ln a. This is assuming that a and b are in the domain of the logarithm function. All right, so we have these properties, and what I'm going to use here, do here on this next one is I am going to change this logarithm function around a bit first so that I have something which is easier to differentiate. Now, whatever the case is, when I'm differentiating and I see a square root symbol, I want to write that as an exponent. But then I'm going to use that first, or was it the third one in that list, and bring the exponent to the front. Okay, so I bring that to the front, and I have f of x equals 1/2 ln 5x minus 7. Well, why would I do that? Because it's something easier to differentiate. I mean, I didn't have to do it, but if I were I'm using the chain rule when I differentiate, and I'm going to have to take the derivative of the square root of 5x minus 7. It's easier to bring that 1/2 to the front. So now when I take the derivative, I leave 1/2 alone, and then I have ln. So the derivative of that is 1 over whatever's inside. And then I multiply by the derivative of what's inside. I might just go ahead and put that in the numerator right away. But this gives 5 divided by 2 times 5x minus 7. All right, so that's just what we can do, and when you have logarithm of a function is you can use some of these properties to expand first. Notice that 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 the property uses the last one, ln of a of t equals t ln a. Now let me go ahead and look at this last one, which I just sort of added to the Openstax list. We have another property that we can use, and we'll use here, which is ln of e to the x is equal to x. This follows from the fact that the logarithm and the exponential function are inverse functions, so they cancel. That's what happens with inverse functions. E to the ln x is also equal to x, even though we won't use that here. And in the second line there, e to the ln x, it requires that x is positive to be in the domain of ln. All right, so this is cancellation properties of inverse functions. Now, what I'm going to do here is, I suppose, first rewrite so that oops, got that wrong. Forgot to write the ln, that's super important. Okay, I'm going to rewrite, so this is ln e to the negative 3x times 2x plus 1 to the 1/2. So all I did is I changed the square root into an exponent expression. Now I'm going to use that top property above here where I have a product. ln a times b is ln a plus ln b. I am going to do that to break this up and expand into two different logarithm expressions. So if there's a property inside the logarithm, that expands to a sum of logarithms. Then I'll use, once again, a property, which is ln and e cancel each other out, and that gives negative 3x. Cancellation between the logarithm and exponential function. I'll use another property where I bring the exponent to the front. So I get plus 1/2 ln 2x plus 1. So that's f of x. That's a lot of stuff before I even took the derivative. Now I'll take the derivative, but those derivatives are relatively simple. Negative 3x, the derivative is negative 3. Come to 1/2, leave that alone. And the 1/2 of ln 2x plus 1, so it's going to be 1 over 2x plus 1. That's the derivative logarithm. It's 1 over everything inside. Then I take the derivative of what's inside, which is 2. Then cancel. And try to write a neat answer. So I'm using properties of logarithms to change the form of my function so that I have something which is easier to differentiate. These are 3 basic problems. The first 2 are from Openstax Calculus Volume 1. The third one I sort of put together myself. And those show some of the ideas behind differentiating functions involving logarithms.